All right, for the second part of 7.4 and the beginning of 7.5, we're looking at higher order derivatives. Remember always that a derivative is just a rate of change. It's a slope or a gradient. Sorry, the notes did not come through real clear on this, so I'm keeping it highlighted in blue here to make it look a little more clear. So remember always, anytime you see this phrase, instant rate of change, that would always mean the derivative. So if you're ever asked, what is the gradient of this function? What is the instant rate of change? That's always the same thing as saying use the derivative to get the gradient. So in looking at these, you'll see the notation on this, and this is something you need to be familiar with, so if you see this on a test, you know what it's asking you to do. But all these are is taking derivatives of derivatives. So if we see a case like this where I have the 2's up there, that simply means to find the second derivative, which means find the first derivative and then find the derivative of that. So as we go through just a couple examples here, so you see this case right here. So that is the original function. If we were to find the first derivative, so dy dx, using the power rule, so you go down each term, 4 times 2 is 8, subtract 1 from your exponent, and you do that all the way down, and this is what you would get for the first derivative. Since this one is asking you for the second derivative, you're going to find the derivative of this, and so I do the power rule again on what I now have, so 3 times 8 is 24, so on, and continue on down the line. Remember, your constants go away when you do derivatives, but this is what our second derivative would look like. With example 2, again, start by finding the first derivative. So derivative of the natural log of x is just 1 over x times 4. Gives you this look right here. So this would be the first derivative. If we bring the x up top like this is a more friendly format for finding the second derivative. So now we can do negative 1 times 4, which gives you negative 4. And then if you subtract 1 from the exponent, we get to this stage here. I always encourage you, because you're going to be doing up to like the fourth derivative on some problems, so you always want to note somehow which one you're on, because it's really easy to not end up on the correct one if you don't keep track. So identify this as first derivative, second derivative, so on as needed, just to make sure you keep things in order. Again, here's one more case. This was using the chain rule that we looked at in an earlier lesson for this chapter. But if I were to find the derivative of this, so you can see we have a function within a function here. So first things first, for chain rule, you start with the derivative of the outer function or the entire function. So remember, e to the 2x, the derivative of that is just e to the 2x, and so you get this, but then you also have to multiply by the derivative of the interior function. So in this case, 2x is the interior function, and the derivative of 2x is 2. So you got to make sure you include him. So that's going to give us this for the first derivative. Now I need to do the second derivative, and again, I have an interior function right here, so I'm going to need to make sure I use the chain rule on this as well. So again, if I did the derivative of this, the outer function, 6e to the 2x, derivative of that would just be 6e to the 2x. So that's what you're seeing right here for the first part. But now I have to multiply by the derivative of the interior function, which again is 2x, and so that's where this 2 is coming from. And so right here we finish it off with that second derivative. Another case of chain rule right here for number 4. So remember, the natural log of anything is just 1 over that term. But in this case, this is an interior function right here, and so I also need to multiply by the derivative of this interior function, which would be 2x, based on that term right there. So we did 1 over the outer function times the derivative of the interior function to get this look here. So now we have a case of quotient rule. So if we're going to do the second derivative, I now have a quotient rule process to go through. So we're doing the bottom term times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And so this is where you get to the second derivative after using the quotient rule. You do want to simplify. This is can definitely go simpler than this. So distribute the 2, multiply right here, and combine like terms, and we can get it all the way down to this stage. And that would be the the best way to leave your answer would be right here. So you could factor out a -2 on this, but that's not really simpler than what we already have. Right here you can see we have a case of product rule. So just to find the first derivative, when I use the product rule, I have my first term times the derivative of the second term plus the second term times the derivative of the first. And if you clean that up a little bit, which would really be just getting rid of that 1 right there. So I have two separate terms. This is my first term, and right here is my second term. So now I have to take the derivative of this. And so these are separated with a plus sign. So we're going to do one term at a time. So just focus in on the first term right here first. And if I take the derivative of this, again, I am using the product rule again on the first term to get this look. And then I separate out and I do my second term next, and the derivative of my second term would just be e to the x. And so those were separated by a plus sign, so that's not going to change. But all this is now my second derivative, and if I simplify that as much as I can, we can get it down to this stage right here. There we go. For part C, keep in mind up above we were seeing the notation with first and second derivatives with like 2's like this. But sometimes instead of a number, they're used with the accent marks. So remember, this means first derivative right here. This would mean second derivative. If you put 3 marks in there, it would be a third derivative, so on and so on. So right down here, like here's an example of a third derivative. They mean the same thing. You could either use the accent marks like this, or you can use real numbers like this. So moving on right down here. So here's a case where we have an original function. If we were going on to find the second derivative, again, same thing as what we just did up top. So you would start by taking your 2/3 times the 27 and then subtracting 1 from your exponent, which is going to give you this look right here for the first derivative. And then second derivative, you just repeat that process again. And so we're going to again do -1/3 times 18 and then subtract 1 from the exponent, and that's going to give you this look right here. So that would be our second derivative. Again, on number 2 here, if we're going to start by finding the first derivative, so natural log of anything is just 1 over that item. Remember, if you have more than just x in here, you have to use the chain rule and multiply by the derivative of this interior function. So the derivative of 3x squared is 6x. So we're going to throw that in there, and that would clean up all the way down to this stage right here. And now if I do the derivative of this, so -1 times 2, and then subtract 1 from my exponent, we get to this stage for second derivative. These can go as far as you want them to. So we have some cases for third derivative, fourth derivative. These are the two most common notations, is either with the prime marks or the number value that you see here. And so we, fifth derivative, so on and so on. These could keep going. As you do something with the higher order ones like a fourth derivative, like I already mentioned, make sure you keep everything itemized for what it is so that you know when you get to the right answer. So for this case, if we just went on down the line starting with that first derivative, so you're just using the power rule on each term. So where you take the exponent, multiply it to the front, subtract 1 from your power. If you do that for all your terms, you're going to end up right here for your first derivative. And I know that looks like it's 10x to the -1 power, but it's really just 10x minus 1. And so that's what you get right here for this stage. So as you go on to do your second derivative, just use that power rule again. So you're starting out with doing 5 times 6, and then subtract 1 from your exponent, and you're going to come out with this line that you see here for a second derivative. Just keep on going. So if I now do the derivative of my second derivative, you're going to get right here for the third derivative. Do it one more time, and you're going to finally end up with a fourth derivative. You may notice as these numbers continue to go down, right, this constant would disappear if I did it again. Then eventually this would disappear. Then eventually this guy would disappear if I do enough derivatives. So there is some limit to certain functions on how many derivatives you can actually do, but other derivatives could actually keep going on forever, such as this one. If you have negative exponents, as I continue to subtract 1, well, I can keep subtracting 1 forever. So from these guys, and I'll never land on 0 since I'm already in the negatives. So this is the case that could keep on going. But starting with this one here, so again, if we start with our first derivative, and you can see by the notation, ultimately we are looking for a third derivative on this one. So we're starting with our dy dx, or you could write that as f prime of x, same thing, but we're finding our first derivative. So remember on this one, you do have a little chain rule going on right here. If this were just e to the x, you don't have to do the chain rule. But if there's anything more than just x going on there, you got to use that chain rule concept to get your derivative. So the derivative of e to the 2x is e to the 2x. And if I multiply times the derivative of my interior function, so the derivative of 2x is 2. Then I go to my second term, and I multiply my negative 2 to the front, subtract 1 from the exponent, and if we do a little cleanup on that, we can write it to look like this. And now I just continue on here. So now if I do the derivative of these two terms, so starting right here, the derivative of 2e to the 2x is 2e to the 2x, times the derivative of 2x. And now if I throw in the second term, so I multiplied negative 3 times negative 2 to get 6, subtract 1 from my exponent, and here we go for a little cleanup here, and you got your second derivative one more time, and you should end up here with your third derivative. So if you want to give that one a try, be a good thing to do. Here's one example of a word problem format of a question like this that you could see. So this is talking about over a 30-day period. It's talking about the water temperature in a pond. So they're giving you the function right here where this represents the temperature in Celsius and T represented time in number of days. So they're giving us the function to start with, and so they're asking us to find the instant rate of change at the end of 20 days and to explain what that means. So as soon as you see the phrase instant rate of change, automatically that means gradient. So use the derivative to find your gradient at a time of 20 days. So if we do what we've been doing so far, if we find the derivative of this, so you can ditch the constant at this point, but if I use my rules on this to find my derivative, you can see on this one that we do have a product rule taking place right here. 8t is my first term, e to the negative 0.3t power is my second term, and so I got to go through with the product rule right now, and so I'm going to do my first term of 8t times the derivative of my second term, which is e to the negative 0.3t, times, and I'm using chain rule here, times the derivative of my interior function, and that's what's giving me this look right here. So this is the derivative of my interior function. And if I continue on with the product rule, so far we did first term times the derivative of the second term plus the second term times the derivative of the first term. And so using that product rule, we come all the way out with this giant look that you see here. If you go through a little cleanup on that, we can work it down to this stage that you see right here. And now if I sub in a 20, based on this, if I sub that in for t, this is what I would come out with. And of course you would do that in a calculator, but this is what you would get. And so if we're asked to interpret this, remember that derivative is a rate of change. So what we are saying on this is that my temperature is changing by decreasing to this amount at the end of the 20th day. And so if we were interpreting that, we would just say it's, my temperature is slightly decreasing based on that number.